Hello everyone, welcome to my section. I will introduce my paper, Unsupervised Face Superresolution while Gradient Enhancement and Semantic Guidance. This video will follow the outline, including introduction, methods, experiments, and application. Now let's start it. Firstly, this paper mainly talks about a popular task, face superresolution, also known as face hallucination. This task aims to reconstruct high-resolution face images from the observed low-resolution inputs. Most previous superresolution methods are trained on paired datasets to reconstruct high-resolution images. However, it is difficult to obtain image pairs of low-resolution and high-resolution human faces in real-world setting. Besides, conventional methods do not fully utilize facial prior knowledge, which is very important for facial structure preservation. To tackle this problem, we propose an unsupervised face superresolution method to superresolve human faces. The overall framework of our method is shown in this figure. First, for a given low-resolution image IX, it is firstly upsampled to IZ by a pre-trained upsample model. Then we design a cycle structure of GZY and GYZ to achieve unsupervised training. The gradient branch G-gradient takes gradient maps of IZ as input to reconstruct a high-resolution gradient map. Then the reconstructing branch GZY concatenates feature maps from gradient branch to recover images with gradient information. Moreover, to recover high-resolution images with sharp edges, we propose a semantic adaptive sharpen module. It is embedded into GZY. This module sharpens facial components with different degrees according to semantic parsing maps, and thus can sharpen different facial regions adaptively. The whole network is trained adversarially. The discriminators distinguish the synthesized data from the real data to improve reconstructing ability of generators. In particular, the proposed semantic guided discriminator DSM can discriminate on different regions respectively, under the guidance of semantic parsing maps. In this way, the semantic guided discriminator enables GZY to reconstruct high-resolution images with diverse details in different facial components. The two major contributions of our methods are gradient branch and semantic guidance mechanism. First, we found that gradient maps of images can reflect the sharpness. As shown in this figure, the gradient maps of high-resolution images are with clearer edges and a stronger contrast between the high and the low intensity. So we hope to utilize gradient information to guide face superresolution process. We propose a gradient branch that takes gradient maps of IZ as input to reconstruct a high-resolution gradient map. The feature maps from the gradient branch are concatenated to superresolution branch. To optimize the gradient branch, we propose a statistical gradient loss and a pixel-wise gradient loss. Second, we propose a semantic guidance mechanism. To enhance sharpness in reconstructed images, we propose a semantic adaptive sharpen module. This module consists of two Gaussian blurring layers to conduct an unsharp masking sharpening algorithm. Given the image feature map, the first step sharpening result can be calculated by subtracting blurry image from the input. Then we divide the image into different facial regions according to its parsing maps. Each region is fed into the second layer to get its sharpening result. Finally, we combine these sharpened regions together to obtain final result of the module. The sharpening parameter of each region is learnable in training process, and thus can sharpen different facial regions with different degrees. Besides, we propose a semantic guided discriminator. It can discriminate on different facial components with different receptive fields under the guidance of facial parsing maps. It improves the reconstructing ability of generators by providing an extra adversarial loss. In addition, to preserve geometric structure, we propose an unsupervised semantic loss. It is calculated on semantic parsing maps. These semantic parsing maps are calculated by a pre-trained semantic segmentation module. Then the loss function used in this paper include adversarial loss, cycle loss, identity loss, semantic loss, and two gradient losses. For experiments, we conduct comparison experiments with several state-of-the-art methods. We compare our method with unsupervised super-resolution methods, zero-shot super-resolution, DS-GAN, and cycle-in-cycle GAN, as well as a supervised super-resolution method, ESR-GAN. We can see from this figure, our method can reconstruct photorealistic high-resolution images, approximating to the ground truth images. The reconstructed images of our method are with accurate geometric structures and very clear boundaries among facial components. Besides, our method can reconstruct images with fine-grained details, such as textured hairs, natural skins, and sharp edges. In contrast, the results of other methods are with low quality and coarse details, even with distorted geometric structures. To quantitatively evaluate our method, we utilize several popular metrics: pixel signal-to-noise ratio, structural similarity, and learn perceptual image patch similarity. Moreover, we use a face alignment module to evaluate the performance of preserving identity information. We extract 68 landmarks from reconstructed images and ground truth images, then calculate mean square error among the coordinates. As shown in this table, our proposed method is superior to zero-shot super-resolution, DS-GAN, and cycle-in-cycle GAN in all metrics, indicating that our proposed method can reconstruct high-quality images with not only pixel-wise accuracy but also geometric structure preservation. Besides, it is worth noting that ESR-GAN is a supervised super-resolution method. Compared to ESR-GAN, our method also achieves better performance on structural similarity, learned perceptual image patch similarity, and face alignment, indicating that our method is comparable to this method treated in fully supervised manner. Moreover, we compare the computational efficiency of our module with other methods. As shown in the last column of the table, our method consumes only a little longer runtime, but can reconstruct images with significantly higher quality than other methods. In order to validate the effectiveness of our proposed method, we conduct ablation studies. We take a cycle GAN model with adversarial loss, cycle loss, and identity loss as the baseline. The implementation details and quantitative results of ablation study can be found in this table. The qualitative results of ablation study are shown in this figure, further indicating the effectiveness of each module of our proposed method. To verify the generalizability of our method, we also implement experiments on real-world images. As shown in the figure, our proposed method can generate photorealistic and reasonable results with very few artifacts. The performance of other methods on real images is not as well as that on the constructed dataset, due to the large domain gap in real-world setting. In addition, we present two applications of our method. First, since our proposed method can reconstruct photorealistic high-resolution images, it can be used as a post-process enhancement tool for image generation tasks. We generate face images through StyleGAN tool with different sizes, and then superresolve the generated images through our proposed method. We can observe from this figure, the images enhanced by our method are almost photorealistic as the high-resolution images generated directly by Style Gun 2. This demonstrates that our method can be used as a post-generation image enhancement tool. Second, our proposed method can reconstruct high-resolution face images from the low-resolution counterparts, and thus can improve face recognition performance on low-resolution faces. We conduct face recognition experiments on low-resolution face images, original high-resolution images, and reconstructed high-resolution face images by several super-resolution methods. As shown in this figure, the face recognition accuracy on most reconstructed images are much higher than that on low-resolution images. Among them, our proposed method achieves the highest face recognition accuracy. This demonstrates that our method can preserve geometric structures and identity information, and thus improves low-resolution face recognition performance. We are glad you watched this video and welcome your attention and discussion. Thank you.